So I'll introduce myself, and I will get a little bit of an overview of where technology has been in the path over the last 40 years or so, but with a strong focus on what's coming next, what the latest innovation has been, and many of those things you have seen and are working in, I hope, these fields, and some other things that you might not have seen yet, but it's coming as well around the corner. Just wait a little bit for it. Let's get started. So first of all, I've been in technology for a very long time, 30 plus years, done almost anything that you can do in technology, I guess, over that time. And right now I am the Senior Vice President for Technology and the CISO for LexisNexis Risk Solutions. As a company, we do a number of things. It's a company that does not provide consumer direct services, so we are not like Apple that you can see or Google, but we provide a lot of services to other companies behind the scenes and many times serving consumers. So even though you might not see us directly, you might see our services the way you interact with your own vendors. And of course, one of our core competencies is data, big data and data analytics. We provide services around risk management and areas like insurance, financial services, retail, manufacturing, etc. Now, just in a nutshell, these are the top things. If you were to ask me what the elevator pitch for our company is, and I promise you this is the last slide I present about our company, this is what we do, the markets we serve. We are a global company. We have all of these information solutions. We believe ourselves to be a technology company. We have been doing technology at the core for decades now, and we built our own big data platform. 20 plus years ago, 25 years ago now, and counting, we built our own big data platform. Well, okay, it's back. Our own big data platform, which we made open source just in 2011. So it's been there, free, open source, and available for everyone. And we'll cover a little bit of that later on when we talk about big data. So let's get started. Many of you, and I see some of you seasoned as I am, might have lived through some of these things yourself. Now, it is a little bit funny and somewhat interesting to see the things represented in time charts that seem to be the ancient past, but many of us live through many of these revolutions across the path, right? I'm sure some of you, I'm not gonna make any pointers there, and some of you on the online audience as well, have lived through the 1980s and our Lisp everything AI revolution back then, expert systems. Many of you have had that boom back then. Later on, the birth of the World Wide Web and the commercial internet, and Sir Tim Berners-Lee involved on all of this. And around the year 2000, when the volume of data accumulated in the internet became enough, the critical mass was reached, many organizations and researchers started to delve into how do we take advantage of this data, how do we extract value, and this is where big data as a term came out. And many of us got involved in that, and that has been a sustained area of growth for technology for the longest time. Many of these revolutions also bring with them a lot of other significant evolutionary improvements. Technologies like storage and compute became quite pervasive as well. GPUs covered a different light. It wasn't just about gaming anymore. Yeah, I know about Bitcoin and cryptocurrency and that too, mining. But all of these revolutions, as I said, also brought a lot of technology innovation along with them. Certainly around the 2010s or so, we had enough, perhaps, with just general big data manipulation, and we started to get into what we can predict from this big data. Machine learning, which was growing at a fairly accelerated pace before, became significantly accelerated, and many of you might have been involved, of course, with the birth of deep learning back in 2008 or so, and how this has transformed I might be using a word that also picks on a pan with transformers, transformed a significant amount of the way we did data processing. And bringing all this to now, you have seen the generative AI revolution, where transformers, the transformer stack in AI and attention-based mechanisms, have really transformed the way, or have really disrupted the way we did data analytics and we do the analytics moving forward, especially in these generative AI models. By the way, if you have any questions or online or here, please feel free to either raise your hand if you're here or post your question in the chat, and I'll be happy to address the question. So, a couple of slides on this platform before we move to the to the other areas of the talk. This is our big data. This big data platform is open source, it's free. It's the one that we have been using for the last 25 years. We developed it originally. We haven't been evolving it over the 25 years. It has, of course, so much built into the last couple decades that is not the same platform we had 25 years ago, as you can imagine. Lots of capabilities coming in, and we are continuing to make sure that we can grow a community, an open source community behind it. This is very important for us as a company because it does ensure that we continue to drive innovation through the platform. I just brought a couple of slides for the platform. This is called the HP Systems platform. It has a couple of main, this is, by the way, a distributed share nothing architecture, like you are used to dealing with Hadoop, Spark, and others. It is all coded in C. The interesting aspect of this platform is that it has its own declarative data flow language on top of it, which is called ECL, and that allows you to express solutions to problems in that declarative manner. If you are a fan of declarative languages or functional programming languages, you might find yourself at home there. And if you know SQL, you might find yourself at home as well, because SQL is a declarative language. We, again, have used this platform extensively across our own company. This is fueling our multi-billion dollars a year revenue in data services, but also many other organizations have capitalized on this platform as well. Again, open source and free, there is nothing to lose. It's in GitHub, Apache license, nothing to lose, try it, lots of resources online. It's, I think it's quite good. You should try it. This is the way we use the platform, and this, I promise again, last slide about the platform. This one shows how we take data. This is the big data paradigm, data on the left-hand side of that funnel, and we drive that data through the funnel as we process the data. We increase the amount of density of information in the data, and we, of course, decrease the volume, and eventually build linking across the data. We identify relationships across data elements, entities in the data, and eventually build a graph. And everything that we create after that, every product, every system, every application that we build is based on that graph that we built throughout this process. Of course, there are lots of components coming in there, not just this probabilistic linkage mechanism that builds that graph, but also quite a bit of machine learning in descriptive and predictive analytics. Not going to get into these details. I think it's quite beyond the scope of this talk. But again, if you are interested in testing a platform that is open source, completely free, no strings attached, you should take a look. It's a good platform for most of your big data needs. Again, questions or comments, please feel free to feed them at any time. Well, and we covered the traditional side of things in the, let's call it, legacy compute environments. And we find ourselves in another trend that has been going on for several decades already. Yes, it might seem like this trend has been going on in the background and you might not have been exposed much on it, but quantum computing, which started as a purely theoretical concept back 4 decades ago, is now quite a reality. Right now, there are quantum computers out there that you can program. And if you haven't had the experience and if you have the interest, you can take a look at IBM's QuizKit framework. You can do all of this online. And not only can you try to create your own algorithm in that quantum computer, you can even run it through either a simulator or the real thing. And you can see what new opportunities quantum computer brings, but also which challenges it might represent as well. And we will get into the opportunities and challenges for both sides, for the legacy compute, legacy sounds very old term, for our standard compute environments and also for our quantum computer environments, and where the intersection is as well in these two technologies. So, what are the recent developments about every one of the things that we mentioned before? Certainly, generative AI is one of those that you can't omit, and you have been on this conference for the past day, and you've seen so much about generative AI already. I was going through the program and seeing how many talks and papers were about generative AI. And one of the things that comes out quite quickly is this ability for generative AI to write code. And yes, today it might not be at the level of writing code that a professional programmer that has been doing this for a couple decades can do. Still, sometimes generative AI makes some pretty absurd mistakes, but it is getting better. And even if it's just as a co-pilot of sorts that can sit on your side and help feed you some of the boilerplate code that you don't want to write, or some of the test cases that sometimes is tedious to write, or document existing code. Sometimes you can feed these models code that you have and ask the model to give you information about how the algorithm works. All of those applications are truly bringing I think, a new way to operate for our software engineers. They can now rely on this junior helper on their side to do many of the things that before took them quite a bit of time. And of course, with the benefit of leveraging something that can give them the answers almost right away, almost immediately. Every time you feed a piece of code or you add a prompt, you will get back the code that you need in a matter of seconds. Another one, if you have been around and you have been to some of the job offering sites, you might have seen this growing profession of the prompt engineers. If you asked me just a year ago what a prompt engineer was, I would have looked at you with glazed eyes without a clue. And nowadays, there are people being hired to do this activity. As you can see, the potential for disruption in the marketplace that generative AI has is quite significant. It already created new professions, new roles, with just a few months of being out there in the public and in the spotlight. Artificial general intelligence. So far, generative AI and our standard discriminative AI, both are what is known collectively as artificial restricted intelligence. They can only work truly in a particular set of problems, and they don't have certain characteristics that would make them more akin to humans. They don't wonder about themselves, as far as we know. They don't drive themselves to things other than to certain optimization problems that you present. So there are still characteristics that are missing there. Those characteristics constitute what is the holy grail of this general artificial intelligence, which is also known as AGI. That is coming down the road. How many years or decades until we get there? I don't know. I will pose a question later on during this talk towards the end, so you can think about it too. But it's coming at some point. Now, we talked about quantum computing. And there are a number of applications for quantum computing that are truly disruptive. The way quantum computers work give us the potential to solve problems that are not solvable in traditional computers. If you have been, if you're acquainted with computers, and I'm sure all of you are, and more than that, you know the limits of our Turing models. You know that there are certain problems that are non-computable in polynomial time. Some of them require much more time, sometimes exponential time, to be resolved. And in many of those, depending on the length of your problem or the complexity of the problem, they might not be resolved in the lifetime of the universe. So there is nothing you can do to address that problem, which might be a curse on one side, but it's also a blessing. Our public key infrastructure is based on those type of problems. The discrete polynomial, the discrete logarithm problem, or the integer factorization problem, large integer factorization, all of those problems are leveraged for PKI, for public key infrastructure. We wouldn't have the secure web that we have today, and our VPNs and our authentication mechanisms, if we didn't have PKI, based on essentially different groups of problems, some of those described originally in 1978, Diffie-Hellman, or 1980-something, RSA. Well, those problems that are very hard with a traditional computer can be made sometimes quite much easier with quantum computers. One of the areas that quantum computers are bringing as a potential benefit is the area of optimization problems, especially those that are known as non-convex optimization, where you have a problem where you have a certain optimization strategy and there are potential for falling in local minima. You need to find the way to get to the global minimum, and getting to that point sometimes takes a lot of time, and even trial and error in traditional computers. Quantum computers might be able to find that global minimum without ever falling in those local minimums. And that is a significant difference to how much we can improve our own algorithms. And of course, this goes hand in hand with machine learning. This is why the field of quantum machine learning is now growing quite fast. Last but not least, I included another area that is also impossible to make tractable in traditional computers, which is the simulation of quantum systems. Because of the way quantum systems operate, yes, you can simulate a small quantum system with a few degrees of freedom, but it's very hard to simulate anything beyond that because of the way the degrees of freedom in a quantum system grow exponentially. But you can do that in quantum computers. You only need a few more qubits, maybe. That makes it quite different, and of course brings a complete new area of experimental physics that we didn't have before either. Pause here, questions, comments so far? Online? Nothing, okay, good. But all of these things that bring such great benefits also bring some dangers, some concerns. I included a few of those on this slide. Certainly, generative AI. We use generative AI every day. I know that I do, for, I hope, good things. But bad actors use generative AI as well for things that they want to get. And many of those are not good. So the fact that we have now technology that gives us so much potential means that we also have technology that can give our attackers more potential. And yes, we could try to adopt a policy of stopping the development of generative AI for those law-abiding citizens that develop generative AI, but we cannot stop developing generative AI for those non-law-abiding citizens, right? So no law will ever help us with this arms race. The only thing that can help us here is for us to try to stay ahead, to know more than the bad actors, to develop technology faster, to put guardrails that can help us make this technology more ethically sound, build ethical frameworks behind it, build controls around it, in a way that can help us get the best of it without having to tolerate the worst of it. Of course, if you have used generative AI, you know some of the problems. Bias in the data can be greatly amplified. If you also take data from humans, and humans have bias, sometimes bad bias, all of that bias can be amplified by the technology. That's a problem. You might also know the issues with hallucinations, where if you train a model in a general way, some of our most common LLMs like ChatGPT, and you try to ask questions about areas in that training set that don't have enough density of information, the model might create answers that are not anywhere in that training set. It comes with something that is not there. It's just not factual. And unfortunately, there is no easy way for you to differentiate between one or the other. Yes, if you are a subject matter expert, you might be able to differentiate that, and that is good. But if you try to take everything that you get from generative AI at face value, you might be in for a ride. So be careful. There are ways to deal with hallucinations, technical ways to deal with them, but there is no known way to eradicate them completely. There is plenty of research in that area, and the field is changing, but still we don't have a complete solution there. Resourceful adversaries. I mentioned some of the issues with some algorithms. In traditional computing, we built all of these ciphers, these encryption, asymmetric encryption algorithms, predicated in these problems that are very easy to solve in one direction and very hard to solve in the opposite direction. If I ask you to multiply two numbers, perhaps not even mattering how long those numbers are, you can multiply those numbers fairly easy. It wouldn't take you much than just a piece of paper and some time, right? And not much time. But if I give you a very long number and I ask you to factorize that number, our ability to factorize that number using traditional algorithms, a sieve or something like that, is not that good. And it becomes worse and worse the longer the number is. This is exactly the problem that we use for our RSA algorithm. That's why you can have a private key and a public key, and nobody can derive your private key from your public key. But quantum computers can do that. Well, they can't just yet, because we don't have the number of qubits that is required to do that for a reasonably sized key length. Reasonably sized key lengths for RSA are 2048 bits. If you use elliptic curve RSA type algorithms, it might be 300 or 400 bits. Still, it's a long number of bits. And you will need a substantial number of qubits to be able to decrypt that we don't have yet. There are some problems with quantum computers, particularly in the area of dealing with noise, that tend to collapse the wave function, and that's a problem. But it will happen. If there is something that history has taught us, is that you can never say that something will not happen. So it's a matter of waiting. Bad actors know that too. And they started to hoard data, encrypted data that has no use whatsoever for them today because they cannot decrypt it yet. Keep that in mind. And certainly, the last one goes to that ethical framework that I was talking about. We need to put some framework around the way we will ensure that technology will sit underneath the food chain, will help us lift everyone, and not displace workers, and not change us in a way that makes us worse, and certainly not controls us if you watch Terminator, so let's not get there either. But building these ethical frameworks is absolutely key. The White House just released, I think it was a couple of days ago, a resolution indicating that the White House is now very decided to build this type of ethical frameworks and these types of controls. Some say that it goes too far, some say that doesn't go far enough, but at least there is not just that, but also the intention to collaborate with other countries. The EU has another initiative, the UK has another initiative. So it is important that as humans, we know what our place is, what the place of machines are, and that make sure that we keep that balance in a good way. Questions, comments? Good. So what can we do as researchers, technologists, educators? Well, certainly, as I mentioned before, we can get better with new technologies. And if we stay on top of them, instead of fearing them, we try to learn how they work, we try to adopt them to a benefit for us, and we try to ensure that we control them properly, well, that can always give us the benefits and minimize the risks that those technologies bring. The other one is cryptography. If you have something to do with saying how things are encrypted, start looking at algorithms that are in the field of post-quantum cryptography. Some organizations and some countries are quite active, the US specifically as well, active in building algorithms that are resilient to quantum computer attacks. Those algorithms are algorithms that can be executed in normal computers, but they exhibit the property that those problems, those hard problems that they deal with to ensure the irreversibility of the encryption, are hard also for quantum computers. Quantum computers use a different type of hardness metric. In traditional computers, you talk about problems that are NP hard, NP complete, right? Non-polynomial. In quantum computers, is what is known as quantum error-bound polynomial problems. And those that are not in that realm are those that quantum computers cannot handle gracefully. And this post-quantum encryption is based on some of those problems. And of course, there are plenty of other things that we should work on as we prepare new generations. Some of us, I'm not going to speak for you, but some of us have been around for some time. Maybe our role is starting to become more to prepare new generations to get in and to eventually take our places. And for that to happen properly, we need to give them the tools, we need to teach them. We need to, personally, we need to adopt the technologies, we need to learn them, and we need to teach them how to use those technologies properly. And I included here a few of them. Deep learning, I think that's becoming quite important for everyone that wants to get in the field. Attention-based mechanisms for generative AI, transformers in particular. But that's not the only framework. There are now new frameworks that seem to be even better and dealing better with some of the problems that transformers have. So there is more there as well. Prompt engineering, even today, maybe in a job, we ask for people that know how to use office tools, Word, Excel. Very soon, we will be asking for people for their ability to create prompts for generative AI in a way that they are effective. So that's an area that is also quite important. And certainly, quantum computing. Yes, I know that this is quite a disruption from the way you think. Many of us who were taught or learned or trained on traditional computers, this might be a slightly different way of thinking, but I think it's important that we start to introduce this in the curriculum in some way. So new generations, the new computer scientists start to understand quantum computers and deal with them, because they will need to deal with them throughout their professional life as well. Now, food for thought. And this is my last significant slide here. So we talked about generative AI. We know that generative AI is essentially these large language models, and we know that some of these models can generate code. Some of them can even run the code. You can feed code to a model and you can ask them to run that code, and it will tell you what the outputs would be or what the result of that code that you fed would be in the normal execution. Now, does that mean that these models are Turing complete then? And this is the question. Maybe they are. If they can run code that any computer can run, well, that's the definition of Turing completeness, right? So maybe these models are already Turing complete. Well, does it mean that then we already designed all of the necessary components to go to artificial general intelligence? If you can tell a model to generate code, and the model can run the code, if you can build a smart prompt that has the right optimization constraints for that model, couldn't you ask a model to write the code for an artificial general intelligence model? Maybe we could. This is probably in the realm of sci-fi now, but it's becoming more and more real. Slowly but surely, some of these models seem to be able to do things that we do, and sometimes they might do those things better. And maybe we already built enough of them for them to take over and take the next step. So, not saying that it's going to happen, but keep that in mind, think about it, and seems to be logical so far. last slide. If there are no questions there, I'll just go through the slide. If there are questions, we can ask them later. We have technologies that would have been sci-fi 20 years ago. If someone asks you if you can ask a generative AI model to write some song or some poem or review some computer program as we have today, that would have been not thought of, right? It would be unheard of back then. Research and innovation. We stand, and this is something that Newton said, how many hundreds of years ago? We stand on the shoulders of giants, right? The more we innovate, the more we build, the more we research, the faster we can research the next thing. And this seems to be quickly accelerating. Now, unfortunately, and now I'm going to take the darker side of this, our ability to comprehend the ethical aspects of the things that we do might not accelerate in the same manner. Our philosophical views of things don't tend to accelerate as much as the acceleration in the pace of technology development happens. So there might be some imbalance there we need to address, but certainly we are innovating fast, very fast. These applications of new technologies are really impacting lives. Today, industries are changing. I mentioned the role of a prompt engineering before, but you can see entire industries now completely changing the way they operate. People are now writing software using generative AI and a few other tools without needing to know software engineering or computer science. And this might fuel new industries. I don't know, just almost every day I read someone writing something, a new game by just writing the rules by hand in English, in plain English, and letting a model take over from there. And certainly we need to stay ahead. If we don't stay ahead, there's a significant potential for misuse of these technologies. We might have problems down the road. Just a word of warning there. Thank you.
Flavio Villanustre.